Hello, everyone. This is Mechanics Inside, and again, this time we'll keep talking about fluid mechanics. In this particular case, about hydrostatics. In particular, we will be interested on the hydrostatic pressure. So as you can see here, we have a volume of some Newtonian fluid, which is at rest inside this container. The only force happening in the system being the gravitational acceleration. As usual, we start from the Navier-Stokes equations for an incompressible flow, which is in this form. The main assumption made is essentially saying that this is an static flow, therefore the velocity field is zero, which immediately implies that the divergence of velocity will be zero. Therefore, this equation is automatically satisfied. And all what is left to be found is just the first equation, which now takes the form of zero equals the pressure gradient and the body forces. Okay? This equation can be rewritten in a component-wise way as this. Right-hand side will have the components of the pressure gradient in a Cartesian coordinate system, and the term which is affected by the gravitational acceleration. In this case, we're essentially taking the xy plane as the horizontal plane and the z direction as the vertical direction. And this is why we have as the vertical direction 0, 0, 1. Doing the component-wise calculations, we see that from the first two components, the pressure, the derivatives, the partial derivatives in x and y are zero, implying that pressure is going to be a function on the height alone. And therefore, once we integrate the third equation, we find that the pressure as a function of z is going to be negative rho g times the height z plus an integration constant c. To find such an integral, such a constant, all we need to do is having the fact that the pressure evaluated at a height h is essentially equal to the atmospheric pressure. Some people take the manometric pressure and the calculations essentially by taking zero instead of the atmospheric pressure. So once you replace the value of C, you can solve for C in this equation. Replacing back in the equation we found, we essentially see that the pressure as a function of Z is going to be the atmospheric pressure, which is constant all across, plus rho G times H minus Z. It's also important to mention that this equation is only valid between 0 and H. Okay? Uh, in a manner to understand how this works, we see that the pressure inside the container is in a front view as we see it here. It's only changing with depth. Basically, what we say is that if you take 2 points, two different points, say like here and here, they will be affected by the same pressure because they have the same height with respect to z. But if you take another point, say here, this will have a different pressure compared to the other ones. And in fact, is this going to be a even higher pressure? That's because the pressure, as I said before, increases in a linear fashion with respect to the depth. So this is some kind of a well-known idea from fluid mechanics. What we're going to do here is just extend a little bit the same idea by considering an accelerating frame in a y direction. Essentially, we say that we're going to take the same container and we're going to move it on the right at a constant acceleration ay. That's why we say that ay is a number, not a function, which is fixed. If that's the case, we can integrate one time, and it's very easy to see that the velocity field of every single point inside the fluid is going to be ay times the time t on the j direction or the y direction if we see here. And it's also important to see that we also have that automatically this becomes the divergence of v equal to 0. So this is again satisfied, and all we're left with is the first equation of Navier-Stokes equations. Now in this occasion, the left-hand side is not 0, but we have the second component as ay. And the same way as we did before, from these equations, we have from this pictorial equation, we have three equations component-wise. From the first one, we immediately see that this implies that the pressure will be a function of y and z, which opposed to what we had before. If you recall, we found that pressure was a function of z alone. But now, since we have this additional component, from here we see that P as a function of y and z is negative rho ay times y plus an integrating constant c. And here we see that the pressure as a function of y and z is then negative rho g plus an integrating constant c. The difference is that this integrating constant depends on c, and this one depends on y. Okay? Because remember, this is a function in both variables. But it's not so hard to check that these two equations imply that what we actually have is negative ay, rho ay times y minus rho g times z plus c, where now this is just a number. Okay? And now, similarly to what we did before, we notice that at the lag point, we have that the height of the fluid, of the column of liquid is h. And so we can say that the pressure, not only at this point, but let's say at this entire phase on the left is equal to the atmospherical pressure, okay? And if we do that calculation, we basically say that P at 0h is negative rho ay times 0 minus rho g times h plus the integrating constant c. And as we said before, this is equal to the atmospherical pressure. And in this case, we solve for c. We find that this is the atmospherical pressure plus rho times g times h, which implies that finally the pressure as a function of y and z becomes the atmospherical pressure minus rho times the acceleration y times y, or we can say plus rho times g multiplied by h minus z. And again, the values of y and z are confined to the domain where these are defined, as similarly to what we did before. Now, it's interesting to see how the pressure works in this different case. Since this is no longer static, this is a volume which is moving, not only moving, but accelerating to the right. We immediately see that whenever you equate this equation, if you say you try to find a level set of this equation, you will find that it becomes a plane parallel to the free surface. What we're saying is that if we were to find another, let's say a different pressure, like a higher pressure, we will find that this is the surface where the pressure doesn't change, okay? So these are the so-called isobaric surfaces, if you will, okay? So along of each one of these surfaces, the pressure doesn't change. But let's say in the vertical direction is where the pressure changes now, okay? These being the unit outward normal vector to each of these planes. And this basically implies a very important, a very interesting result, which is the main goal of this video, in which we say that the hydrostatic pressure is essentially depends, or the hydrostatic pressure depends on the frame, depends on the frame of reference, okay? What we say is that if our frame of reference moves, then the pressure can change, as you can see. It is no longer the same, the trivial case we have in here. This is now a different and a more general way. And so as you can see, pressure now is not parallel to the ground. It's more like in an inclined plane, which is found by taking the components of G and AY in some way. And also an important, consequence of this is that at zero gravity, or we can say when equivalently when the acceleration of the frame equals to the gravity, the negative of the gravity, there is no hydrostatic pressure. Okay? And that's essentially what we see, for instance, on the International Space Station. All right? So it's really interesting how a simple concept that we take for granted is essentially much more general than what you essentially think. Okay, so this is all I wanted to tell you this day. If you want to see some more interesting facts and more interesting phenomena in mechanics and continuum mechanics in general, and particularly thinking on fluid mechanics, solid mechanics, thermodynamics, heat transfer, and let's say everything which is in between, well, you can just follow our channel, and so we will keep working on these very interesting topics. So see you next time.